Hi, thanks for joining us today. My name is Daniel Toms, and with me is Ben Wilson and Jazz Bali. We're the core developers for Databricks Labs AutoML Toolkit. I'll be starting us off today talking a little bit about the high-level introduction to AutoML Toolkit. Then Ben will go into a deeper dive on some of the great features that we have on the feature engineering piece. Then he'll go into the core tuning algorithm a little bit and talk to you about the roadmap and what's to come in the future. And then Jazz will clean us up and finish us off with a end-to-end demo showing us how it works from start to finish and show you what AutoML can really do in production. So without further ado, we'll just go ahead and get into it. Okay, so to get started, when I think Ben's built this a few times probably, and to get and when he started off, he and I were working together, a little bit after he got started on this idea, and we had a few goals in mind. The goals were to simplify that feature engineering and that all that trivial boilerplate code that you copy and paste from online every time you start a model. We also wanted to be able to get to something real and something that was somewhat usable faster. That way that you could kind of get going and see if you had even an idea that was worth pursuing. After that, I think Ben's brain went off the rails and he started creating all these new crazy ideas and started adding them into the code base. And they were crazy ideas to me, but I guess they were things that he kind of had built several times in the past. And as some of those features started to come into the code base and I started to use them at customers as his number one champion, I I started to actually get pretty good results. And we knew we had something when we started to outperform data scientists at our customers with this tool set. And this was over a year ago. And ever since, we've had opportunities to explore this at different customers, and it's only been improving ever since. Then about a year ago, Jazz came online and said, "Hey, I want to improve this and help you guys develop." We said, "That's fantastic. Come on." And so Jazz then was introduced to the team and started to work with us and develop the pipeline, which I'll talk to you more about later. This is great because it helps us to track and reproduce results very easily. Okay. So the AutoML toolkit has a lot of different features, and I'm not going to run through all of these today because you can read. And they're all documented really well on the online. You can find this and all the information at github.com/Databricks Labs. And there you'll see a lot of all the labs have been published by Databricks publicly. And then you can actually grab the AutoML toolkit, whether it's the jar, find directions to how to get it on Maven, or get to the documentation. The documentation is very extensive, so I'll spare you this today. And as I said, Ben's going to be talking a lot about some of those features as well. What would AutoML be without some model selection and model tuning? So obviously that's included, and Ben's going to talk us through some of that in a few moments. But basically, this is the progression of model selection, tuning, and some of the extra features that are in there. This model selection process actually also allows you to employ really great steps, really great features like auto stopping to save you some money and time when you're training your models. It also does a really nice other thing, which is to excuse me is to explore as much of the hyperspace as possible. So when you pass in your hyperspace parameters, it's going to maximize your coverage of that exploration to make sure that we find the uh, real global minimum as best we can. Then it also includes an inference pipeline to simplify scoring. And one of the things that we wanted to do as we progress this is to make it very simple to hand off between use cases, between teams, and to DevOps when you're ready to productionize. It's also not realistic to try and do that all without any tracking. The number of versions between features and models is extensive. And it really impossible to track all the different experiments across all the teams without some kind of tool. And that's why we integrated directly with integrated directly with MLflow using the model tracking toolkit that we have through MLflow. We support several models, and they're really the base ones that are supported in Spark. We might be missing one or two here, but for the most part, these are the most common in Spark ML. And I'm going to show you some ways to even use models that are not included in Spark ML and how AutoML can help you with that as well. In my opinion, one of the greatest features of AutoML, even though it's probably not Ben's, but my favorite thing is that you can actually override the configs and you can actually make it your own very quickly. So the idea here is to, at the team level, at the organization level, or the use case level, you build up a strong baseline default of all the configs that you need. From there, you just use them and override them where necessary. This makes it very easy to reproduce results and track it through the pipeline and through the process. And yes, there's Python. So we do have a Python wrapper, thanks to one of our colleagues, Mary Grace Moesta. And you can see an example here on the right where there's an example of the Python, and this is end-to-end implemented at a customer. And you can see that it's only a few lines of code. Most of the lines of code are the imports and the data acquisition from the source. The AutoML stuff is very, very small. And that was the goal. So as you can see here, we actually just overrode a few of the defaults here for this customer. And because we were doing a test in this example, this is what we needed to override to do a few tests and see if we could improve our results. And then this is what it looks like when we are ready to hand it off to DevOps. You just submit a ticket to the DevOps team with the MLflow run ID, and they can take it from there. This is also how you can share your results and your models with other people as well. What I'm going to do for the remainder of my time today is demonstrate how you can decouple your workflows to save time and money. There's a lot of work that goes on before model training. And in fact, as it's been shown on many of the slides and stuff I'm sure you've seen this week, there is a lot of work, and most of the work, in fact, actually happens before the model starts. That's where a lot of the money goes into the feature engineering pipelines and the feature importances selection, feature selection, and then a lot of those testing. So what we don't want to do is rebuild our features every time we want to run a model, and we don't also need to select new features every time we run a model. So the pipeline in AutoML Toolkit allows us to separate those things, and I'll show you that in my demonstration. Today for the demonstrations, we're going to be using the wine dataset. The wine dataset includes 178 instances of wine. Those are the attributes, I think, across 13 different attributes that will help us determine, that helps people determine whether the wine is going to be good, bad, or ugly. Those are represented in a class of 0, 1, or 2. This makes it a multi-class problem, and we're going to explore that today in AutoML. As I've been doing some of these demos throughout the challenges we've had in the world the last few months, I've begun to notice that sometimes it's really easy with editing and other things to forget to really explain what you're doing. So I thought I'd take a moment and actually explain what I'm going to do so that it makes more sense and it's easier to follow. First, I'm going to load some data. Then I'm going to prep that data for the models. I'm going to then improve it with some synthetic data that's going to be generated through some of our features in AutoML Toolkit, such as feature interactions and smoke. Then I'm going to identify the most valuable pieces of data that's going to help us, and so we can reduce our noise and ultimately improve our result. We're going to then train a bunch of models, and then we're going to get some awesome results. With that, let me go ahead and kick off the demo. Hey, thanks for joining my demo. Welcome to this. It's kind of weird doing the recording, but bear with me, and together I think we'll get through it. So, just to get started here, I want to show you a little bit about the setup. Really what I'm going to show you right now, because of the time constraints that we have, is these imports here. Jazz is going to talk more about this stuff in a little bit. So to get started, I'm just going to run this, and I'm going to set up a few configs that I'm not going to go into right now because it's more than we have time for. But set some configs up, and now we're going to get some data. This is the wine dataset. What we're trying to do is predict the class. So this class will be predicted based on these attributes of a wine as being good, bad, or ugly, I guess you could say. The next part of the process is to start to scrub your features and prepare them for the model that you're going to use. And granted, different models require completely different types of feature engineering, but in this case we have a couple of trees and one logistic regressor that we're going to use to be a classifier for us. As you can see on your screen here, and as we mentioned earlier in the presentation, there are a lot of feature engineering features that are included inside of AutoML. And so I encourage you to look at those on your own time, and there's tons of documentation as we talked about before. But in this case, we're just going to use 3 different types of feature engineering for this and 1 split feature. So the first 3 is just filling our NAs as we always have to do. We can't send nulls into the model, right? So there's that, and then we want to make sure that any columns that don't have any variance, we remove those, which obviously this data set doesn't. And then we're going to turn on something fun here called feature interactions. That's going to enable us to generate some synthetic data if there are any features that are interacting. And Ben's going to talk a lot more about that in a little bit, so I don't want to steal his thunder. And he's going to do a lot better job explaining it than I will. So there's that, and then the last thing is we're going to split it. There might be a little class imbalance in here, so we want to make sure we split it, but we split it in a stratified way so that we keep our labels consistent. So we're just going to go ahead and kick this off. It should run pretty quick here, and if it doesn't, we have the magic of editing, right? But all we're going to do here is just generate a config, and we can talk more about the config later, but the config is just a set of overrides that we can do from defaults. And so I have a few pre-configured here, not many, and you can see some of them are just right here. It's just a map that specifies some parameters for us. So in this case, I'm just going to take our defaults for XGBoost, as that's what we're going to use to identify our feature importances as per the splits on a trained model. Okay, and then we're going to just override some of the feature engineering pieces that we want to enable. And essentially what we're going to do is we're just going to run through and do those pre-steps before you can run any models. Then we're going to repartition and store it in cache. And if you look through here, you can see all the details about what happened, the input-output columns. But one thing that I want to call your attention to is that now we have 92 columns. Well, we have a couple more than 92. But before we only had 12. So that's the synthetic data that was generated based on the feature interactions that were identified. So that's a lot based on 12 features to generate 92. So probably not all of them are necessary. But just assume that they were for the moment, and in the event that they were and we wanted to reuse them several times later, we could actually save this data frame down. And when we save it down, we're going to be able to pull it back in later and train models that don't even exist and are not supported inside of AutoML. And you're going to be able to send them to things like GBM or elsewhere to do other kinds of specialized trainings on them. But this allows you to do your feature engineering in this format in a fast pipeline type way. Okay, so back to the 94 columns that we have here. Now, it's basically the original columns that we had, plus a whole bunch of feature interactions that were identified, and then we have our feature vector. So essentially, it's the same columns with the feature interactions and the feature vector, where any of the feature engineering that we did to the columns are going to be already done in the feature vector. So we don't probably want all 94 of those columns, as it's going to create a lot more noise than what we want. And as such, we're going to try and identify which of these feature interactions are the strongest and are providing the most signal, basically the most new signal to our data set, so that we can best predict what type of wine we're going to have based on those attributes. Okay, so the first thing we're going to do is we're going to kick off this feature importances run, and while it runs, I'll talk to you about it. What we want to do is minimize that noise, those features that don't actually give us any value. We want to take those out. So to do that, we're going to train an XGBoost model, and from that trained XGBoost model, we're going to use its splits to identify which features are most important to deriving that predicted value. So we'll just watch this churn here, but a few notes. I have a few extra overrides here, and what I'm doing is I'm turning off that feature interaction flag because we already have those features, and then I'm just keeping the stratified split, and I'm going to go ahead and turn on auto stopping here. So once we get to 98% accuracy on this model with all those columns, I'm just going to go ahead and stop, make it go faster, and save us some money. All right. So just like before, we generate our config from those overrides, and then we wait for this to train. And hopefully it won't be long because maybe it will find an answer early. But either way, you just kick off the feature importances run through this API endpoint here. I'll be back with you once this is done. Okay, that didn't take so long. So we trained through what looks to be about 2 generations of optimizations for this genetic algorithm, correct? The second generation here. And through that, we identified some features that, hopefully we identified some features that were valid for the prediction. So first, let's take a look at them. So we can do that just by looking at the importances. And here are the columns that were identified as relevant. And quite interestingly, we see that there are some feature interactions that are helping us to derive our value. And whether or not we hit 100% accuracy or not on this, I don't know, but you can see the scores here, and we could also check them out in MLflow, but we'll demonstrate that a little bit later. Nonetheless, we definitely hit at least 98, and there's our one, so we did actually get a run with 100% accuracy with all of those columns. Now, of course, I didn't do a whole lot of k-folds, and and I didn't do a holdout set and do all that. So it's probably going to be a little overfit, but this is feature importances. They won't change that much. So yeah, it's a little overfit for sure, but we're going to take out a bunch of those columns. So that's what we're going to do next. We're going to identify these columns that are valuable for us, and then we're going to select only those columns. So now we're back down to basically what we started with, 10, 12 columns, something like that. However, now we have the columns that are identified as the most important. And we generated these columns here, these feature interactive columns. Before we kick off the main run for the training of all these models, I want to note something that we're going to do inside of these models. One of the overrides I have specified here is to enable k-sampling or SMOTE, and that's going to generate additional synthetic data. Before we generated synthetic data on the column layer, now we're going to generate synthetic data on the row layer through some fanciness. Now, I'll let Ben cover this because Ben is going to cover k-sampling and SMOTE as well, but I want you to see how easy it is. You're not seeing anything about k-sampling and SMOTE. They're complex ideas and hard to implement, but you're not seeing anything about it. Literally, inside of these configs, all I have is k-sampling, split method set to k-sample. So now we're going to go ahead and kick this off. But I'm going to do a little time lapse here so you can see it train, but not to sit here and listen to the crickets. And I'd love to play some music for us, but I don't know if I have licensing or copyrights. So we're just going to sit here and I'll speed it up so it's not extremely awkwardly boring. But before we got started, I thought we would share a few goodies. Here there's a starting generation, so this is a genetic tuning algorithm. So that's the generation, and then below you can see some of the configs with regard to the hyperparameters that are set there. And there are a lot of other things going on, and this is where like the standard output is for everything that's going on during the training cycle. And this is actually quite interesting, and I sometimes just sit there and watch it for a little bit to make sure that my model is working okay. So this is a really valuable piece, as it can help you understand what's happening under the covers while your model's training. So without any further ado, let's go ahead and speed this thing up. Okay, so back to real time. This is XGBoost training finishing up here, and you'll notice at the end it's going to spit out some a little bit different data, and then it's going to switch right over into random forest because that's been tied into our config there. As you can see here, the random forest config is just alongside the XGBoost config, and Jazz is going to talk more about the pipelining and stuff. But yeah, this is going to help us a lot when it comes down to running one model and then running another and then another and testing them all with their own hyperparameters and whatever to ensure that we can turn it on at night and walk off and come back tomorrow and have it done. So with that, we're going to go ahead and speed up time again and watch the rest of the training. Okay, now that all the models have finished training, let's take a look at what actually happened. So to do that, I'm just going to pop over into here and look at my results. And I'm going to go to my best results. Jazz will show you more about MLflow in a minute. So here's my results. I can just take a peek at them and compare them. But for now, I'm just going to note that several of them, I think the random forest and the logistic regression, both hit 100% accuracy on this, and it was pretty quick, and I have about 16 cores on these nodes. So now we're going to head back over to our main notebook here, and we're going to kick off the manual version of what we just did, but a very small scale of it, and we're not even going to do grid search or anything like that. We're just going to run two models. We're going to load the raw data set. We're going to run XGBoost and random forest, but this typically winds up in some kind of loop with grid search and everything else. And I just ran this, and it did finish really quickly because it was just two models on 178 rows. So it did run really fast. But I just wanted to note the scores here. The scores here are, we got a random forest of like 0.15 weighted PR versus our 1.0, and XGBoost of 0.15 versus AutoML's first couple minutes out of the box running 98.8 or whatever it was. So you can see it's clearly much faster than writing all this code and then trying to do a grid search. You just pop in your config, override a few here and there, depending on what you want to do, and you're off to the races. All right, and as you can see through the demo, I did exactly what I said I was going to do. We loaded the data, we prepped it for its models, then we improved the original data set through feature interactions and SMOTE. We identified the most valuable data and reduced the noise. Then we trained a whole bunch of models and we did get some awesome results. So thanks for that. And with that, I'm going to go ahead and turn it over to Ben to do a deep dive on a few of the pieces of data of AutoML.
Hi, I'm Ben Wilson, practice lead on the RSA team, working with Dan Tomes. And as Dan mentioned, we built a pretty cool team here with the developers that are on this call. We also have a couple other people that have contributed to this project, and it's been a little bit more successful than we thought it was going to be, which is kind of cool. A lot of customers are using it, but more importantly, people are able to scale their machine learning teams with automating some of the more annoying parts or annoying modeling that people sometimes have to do. So what I'm going to be talking about today is, as Dan mentioned, I'm the resident nerd of this group, the algorithms dude. So I'm going to be going through a couple of those things that Dan showed off, particularly what case sampling is, why it was built, as well as the feature interaction aspect of this. And we'll do a quick overview, high level, or maybe mid level, of what the actual tuning algorithm is, how it differs from some of the other ones that are on offer in the space, and why it might be more successful for some of your use cases than other ones you might have tried in the past. We'll also talk about performance and how to melt copper on a cluster. So the first thing we're going to be talking about is case sampling. And we're going to, before we get into the details of it, we're going to talk about the different aspects of how we can split a classification task up for training and test for validation throughout AutoML. So for classification tasks, and we'll talk about regression at the end, but for classification, there's four main ways that we can actually split our train and test so that we can actually use AutoML to do hyperparameter tuning. Now, there's a fifth one that's not listed here, which is random. Random is, as it implies, it's how typically most people do splits, where they're saying, just give me some random values from my data set, and I want 80% in train, 20% in test, or 70-30, whatever you so choose, and it'll just randomly pick that, in which that's completely fine for most regression tasks. But for classification, you run the risk of selecting too few samples in either train or test of a potentially minority class. So what we implemented over a year ago now is a stratified split. That's the first sort of approach you should look at based on class imbalance. And this is either through a binary or multi-class classification task. The stratification is going to look at your data. It's going to do some approximate counts of how many of each class that you have. And it's going to try to split that in accordance to those ratios, so that if you have 90% of your data is class label 0 and 10% is class label 1, it's going to maintain that ratio in your train set. So you'll still get that 90-10 split between those class imbalances. This also works for more complex multi-class classification, where you might have 70-20-10 split between your classes. It'll look at that and it'll intelligently sample the data to make sure that you have that same balance between train and test. Now, it's all well and good until you look at some of the use cases that people use for binary classifiers, in particular for stuff like e-commerce and financial services, where you're trying to do a classification on a fraud model, where unless you have a really terrible business model where everybody's trying to steal your stuff, you're usually going to be looking at fraud rates that are, you know, fractions of 1%. And traditionally, how people have handled that is this second item, which is under or oversampling. Now, undersampling is taking the majority class, the not fraud in this case, and reducing the row count of that. It's considered a destructive task because you're removing signal from your actual model training stage. And for some use cases, that might be fine. People have kind of adapted to that over time, but you're losing signal. And the reason you're doing machine learning on Spark is so you can use all the data that you have available to answer your problem and get a good model. So we're not going to really talk about that too much. It is available if you choose to use it, but there's some drawbacks to it. The other problem is people trying to boost the minority classes by copying or replicating the actual signal. So you take that 0.1% of that minority class and you just copy that data 50 times to try to give it enough row count so that the actual classifier can learn that information. That introduces a whole different problem, which is bias in your model. So it's going to learn that one class with those particular characteristics really well. It's not going to adapt to unseen data that well. So you may get okay results on a test set while you're doing hyperparameter tuning, but then when you actually run it in the real world or against holdout validation data, it might just completely fall apart. So you could get a really good accuracy or an F1 score, but as we all know, those are kind of garbage on class imbalance. So in a binary classifier, you're going to look at area under ROC and you're like, wow, I got a 99.1% area under ROC. It's because it successfully classified the 99.1% of zeros, and it could not learn the minority class. So that's also kind of bad. We also have a chronological split, which allows us to set a date or a date time field, and you can specify a percentage of the distribution of that time series to make a split or a cut. It's mostly used in regression problems. We're not going to be talking about it too much, but that's also there. What we are here to talk about is what Dan already showed and what Jas is going to show also in his demo, which is K-sampling, which means almost nothing to anybody in this audience, but what it is a distributed implementation of SMOTE. So at the root of what SMOTE uses to determine how to actually build these synthetic data is KNN. And KNN is a great algorithm. It's far more accurate than using some of the other algorithms that are out there for clustering, like k-means, because it's able to do the associative distance measurements between elements within your data set. The drawback to KNN, though, is that all your datas have to be on the same physical machine. Now, people have tried to do and implement SMOTE and get it working on Apache Spark on a big distributed system. The problem is that it's very not performant when you try to implement this algorithm. The reason being is because you have to move all the data from all the executors to all the other executors. So you need this consistency of state on a single physical machine in order to do that calculation. So lots of shuffling, very expensive, takes forever on runtime. So because that's not really an option for us, what we decided to do was think about what is the actual solution that we're trying to achieve here, which is synthetically generate data that is similar to other elements of these imbalanced minority classes, but how can we do it in a distributed manner? And I spent about 6 weeks breaking this 1,000 different ways before I finally figured out a way to actually do this that actually works, shockingly. And we're going to go through the steps right now about what this algorithm kind of does at a relatively mid-level. So the first thing is this happens after we've already generated our feature vector. From all the processing steps that happen, we're indexing strings, we're creating one-hot encodings, whatever we're doing in order to create that feature vector. This happens right before we're going to go into modeling. And it's going to take that feature vector, regardless of if we scale it or not, and it's going to apply a scaling. And this allows us to constrain the space that we're going to be searching and normalize the data so that the distance measurements that we're doing throughout K-sampling are actually not influenced by varying degrees of magnitude of the doubles that we're looking at within those vectors. So we scale it, Then we build a k-means model, which is a distributed algorithm. We're just using Apache Spark ML library to do this. But the reason we're doing that is because we want centroids. And those centroids, we want to be able to look at the data frame after we've already transformed it with that k-means model. And we're going to go through a quorum voting algorithm. We're going to say for each of these k clusters that we have and each of these centroids, determine which ones most accurately describe the minority classes that we want to boost the signal of. And we're going to go through iteratively until we vote on a candidate pool of k clusters. Then we're going to get those centroids from those k clusters. And from those, we're in sort of in series, we're going to be building a min-hash LSH model, which that's going to allow us to do a rather efficient distributed means of getting distance measurements. So we're going to apply the centroid vectors into the min-hash LSH, and we're going to attempt to find nearest neighbors to those centroids. So it'll search in the n-dimensional space around it, and it's going to capture all the minority classes that we're interested in. We're going to collect those vectors, and then we're going to recurse over those vectors, those candidate minority class that we already have that are real data. And we're going to start mutating them with the centroid value itself. And that's done through there's a number of different parameters that you can tune in AutoML to control how that behavior happens, whether you want to fully randomize it or you want to control in a linear manner just a couple of the actual vector positions to mutate within that dense vector. Once we're done with all that and we generate either a complete match to the minority to the majority class, or we hit a percentage, which from me, the person that developed this, I do recommend using a percentage. Don't do a match on extreme imbalance, or you're going to need a bigger boat. It's going to replicate your data up to that point, and you could double your data size or even more. So usually a percentage of that, get it so that it's not such an extreme class imbalance. And once you get that, those number of synthetic rows that have been generated, we're going to flag all of those. The reason we need to flag them is because we cannot test on those. We can't use them for validation. That would give us an incorrect score. So what we want to do is only apply that to our training set, but mark them as synthetic, so that all the following stages, everything in the pipeline that JAS has built and is integrated with, all of that is ignoring those rows of data. It's just for the algorithms to tune against to get more information. And this is a visualization of exactly why we built this. So this is a typical data set that I've seen at many customers who are trying to do fraud detection or trying to detect some sort of anomaly in their data, and they're using a classifier approach for it. It's really hard to find that signal, and this is kind of showing just how much of an imbalance that can be. So with K-sampling, we can take those red bars and we can bump them up to a certain percentage so that we can learn that signal a little bit better. The important thing is in the validation stage, we're not bumping that bar up, because that would be sort of unethical, and we would get a synthetic score that's not, reflecting the actual data. Another thing that Dan talked about and showed off in his demo, and something that JAS is going to show off as well, is feature interactions. This is something that a customer actually asked me a question about because they were doing this manually. And they actually convinced me through showing their results that this is a really cool technique, particularly if you have a sort of a problem to solve in machine learning that you can't use ensembles due to explainability concerns, or it's just too much of a runtime impediment when you're doing inference to use some sort of stacked ensemble method. So they showed me, hey, all we do is just take a product of these things, of each of the features that we think are going to be important. We score them, we validate them, and then we manually put them into our data science ETL pipeline for feature engineering. Then I went off and did what I normally do, which is read a bunch of papers and look at a bunch of blog posts and ask a couple of people and say, hey, have you ever done this? Turns out there's a couple of people that I asked that actually said, yeah, this works pretty well in some use cases, but it's kind of hard to control what you're actually introducing. The one thing you don't want to do is just blindly add everything, because you can introduce so much, noise and variance to your signal that you can get some really bad results and destroy your model. So I said, okay, I'll build it 3 different ways. But the important thing is this is not something that we built from scratch. This is implementing something that other people have thought of. We just did it in Spark. So at a high level, this is what's actually going on with feature interaction. We're taking each feature from that data frame, from that feature vector that we're about to create, and we're going to just multiply them together. And we're going to create a hybridized feature. So we take feature A, feature B, multiply them together, we get feature AB. Then we're going to use basically what decision trees use for their validation steps. So if we're doing a classification problem, we're going to calculate entropy on a split criteria. We're going to say, how important is this feature for explaining basically these classes that we're trying to predict. So it's kind of on a decision tree. It's the first layer, the first round of splits that we're doing. We're not actually recursing down through the tree and doing repeated splits like we do with decision trees. We're just doing that first layer. And we're calculating entropy for classifiers. We're calculating variance for regressors. And we go through and do some checks, which we'll talk about on the next slide, about which ones to keep and which ones not to keep based on our settings. So as I mentioned, we have this different modes that are available for feature interaction. Now, the one that I recommended not to use is, of course, in here. It's definitely not default, but it's the all methodology. And that's if you're doing something like what Dan was showing, which is I want to do feature importances. I want to just see what the results are for everything that I could possibly test. It'll do with the interactions of every single feature to every other feature. And then you can evaluate it statistically. You can do your own tests. You can see, oh, there's some sort of signal here that I didn't think was there. So it's an information exploration tool. For all other cases, we have by default optimistic set. So if you turn it on, you don't override anything. Optimistic is going to go through and it's going to check each candidate. So the dot product features, the feature A underscore B that's created, it's going to get the actual information gain scoring from that split. It's going to compare it to both parents. And if it's as good as X% of the information gain of its parents, either one, either A or B, it's included. That's optimistic mode. Strict mode is a little bit harder to actually get interactive features to be a candidate. And what that's going to do is still going to do the same check. It's going to check A underscore B to parent A and parent B, but it has to be X number percent as good as the information gain of both parents. So it's an and, right, Jess? All right, so the final thing that I'm going to talk about is going to be how this thing actually works from a geek level. And there's 4 main stages that occur within AutoML for its tuning algorithm. The first one is seeding a gene pool. And what this is going to do is explore through permutations of a search space that's defined. And these are things that you can actually override or just leave the defaults. We have ranges that are set for each algorithm on each of the hyperparameters. And we also understand what the distribution type is of those hyperparameters. Some of them are normally distributed, linearly distributed. Some of them are exponential, some are logarithmic. So we capture that search space that we're going to be looking at, and we generate a bunch of hyperparameters. We then, and you can control how many to start from that initial gene pool. Then we actually start running these, but they're all run in parallel. So we create a new fork join pool. We set a level of parallelism that occurs. The driver will then asynchronously through futures kick off a bunch of modeling runs on the workers. These will return out of order. They will return when they are done doing what they're going to do. As one returns, another one will start up because the fork join pool can process just that number of what you said is parallelism to execute concurrently. When all of the models for that first generation have been completed and they return back their results, we then go into the evolve stage. What that's going to do is take the top N models from that preceding layer, and it's going to generate a bunch of new things to test. And then it's going to mutate the best conditions from the parents that were retained from the previous generation with these new synthetic hyperparameter collections. Then it's going to go through the same process as the first one did. It's going to asynchronously kick off n number of these in parallel. When all of that pool finishes and returns, we go to the next stage. And you can set through configuration how many layers of generations that you're going to test in this manner. And there's other settings that you can say, I want to reduce the amount of search that happens each generation. I want to mutate less and less in order to try to converge on the best condition. And after we're done going through all of those generations, we're going to basically gather all of everything that has been tested, as well as the metric that you're scoring against. And it's going to create a relatively large data frame that we can then train a linear model against. And this linear model is going to be used to attempt to figure out what the best optimized parameters are across the entire search space. And we do this by generating a truly astronomical number of permutations of hyperparameters through a synthetic data set. So by default, I believe it's 400,000 rows or 400,000 combinations of hyperparameters are generated. You can take that all the way up to a couple million if you want. You might not want to do that over about 2 million, but it'll generate a lot. And then it'll apply the model that it trained on our a priori results that we got from the genetic algorithm to try to predict what is going to be the best result of hyperparameter combinations. And then we actually take n number of those predictions and build those models. So that's the final training stage, the final generation. And once that's done, hopefully we get the best model that we can. Now, finally, I'm going to talk about a couple of the new upcoming features that we have that are sort of planned on our roadmap. One of them, and I alluded to it before, which is stacked ensembles. And we already have the POC done of that, sort of the MVP. It's not in the AutoML toolkit yet, but we are working on it. And this is going to allow us to do a bunch of weak learners of differing model types into a first layer. And these are all going to be tuned through AutoML. So we're going to get the best possible model that we can for the first stage of that. And then on top of that, we're going to take those pipelines, we're going to glue them together into one big master ensemble pipeline, and then throw an additional either regressor or classifier on top of the predictions of those. And based on our testing, it beats everything that AutoML can do on its own as of right now. So it's definitely something we're excited about working on and pushing out to the public with that. The other thing we're working on is an improved method of the slide that I just talked about, which is genetic algorithm 2.0. And one of the things that we want to do is implement something that is pseudo SGD based. So when we're actually searching for candidates in each subsequent generation, we want to make it a little bit more intelligent. So we want to predict where on a fitted curve, the next set of hyperparameters should be tested, and also search for spaces within that search space that haven't been adequately tested yet, so that we can explore the space more comprehensively before that final tuning phase where we say, give me all the data, now tell me which one's probably going to be the best combination. And the final thing, it's currently partially in AutoML, but there's no public facing API for it, but we are slowly adding to it. And it's something that is going to help out for some of the stuff that Dan was showing on his demo, which is we generate these features, how do we analyze them correctly, and how can we get better visualization and statistical readout reports from things that data scientists care about. Stuff like, I want to see my relationship of correlation. I want to check my covariance reports. I want to do an ANOVA on my data for a particular column based on my class labels. I want to see, is there a strong signal here that I should be focusing on and building additional feature engineering steps before it even gets to the toolkit. So we want to sort of give out those tools to the ML community to do this stuff on Spark without having to revert to subsampling the data to such a small degree that you could actually lose some of the information that you're looking for. And also stuff like automatic PCA analysis of the feature vectors to determine if this candidate feature engineering set where you're trying to push through AutoML is even worthwhile to try to predict what you're trying to predict and see if there's an actual signal there. So on that note, I'm going to turn it over to Jas for his pipeline demo of his awesome code base.
Well, thanks, Ben, and thanks, Daniel. That was awesome. Hello, everyone. My name is Jas. I'm a senior solutions consultant with Databricks and also a core developer on the AutoML code base. So for the next demo, I'm going to be walking you through some of the stuff that Ben talked about and also show you how simplified it is to build self-contained prediction pipelines out of AutoML code base. Let's get started. All right. For the next 15 minutes, I'm going to talk about and walk you through AutoML's family runner APIs, and we're going to see how easy it is to productionize your AutoML pipelines. Let's start with getting some data set. In my case, I'm going to use wine data sets published in the UCI machine learning repository, and I'm particularly going to use wine data set because who doesn't like wine, right? All right, so let's look at what the data looks like. So in our case, it looks like contains some chemical analysis of wines, around 13 feature columns, and we are predicting what particular grape wine this wine belongs to. So that's what our data set is. Next thing we are going to do is import few important classes from AutoML library. As you can see, there are 3 classes that I'm importing: configuration generator, family runner, and pipeline model inference. For configuration generator, it's gonna be helpful when we have a map of configurations and we want to convert that into an immutable Scala object that is then fed into the family runner to run our modeling part. So the next class is the family runner. It's the main entry point into using any of the pipeline APIs. And then the third class is pipeline model inference, which we are going to use to do some loading of pipeline models to do inference. And then the next part is initializing few multinomial classification tasks here. So what we are doing here is, as you can see on my screen, I'm going to train and optimize 4 models using AutoML: logistic regression, random forest, decision trees, and XGBoost. In my case, I'm defining 2 configurations. The first one is, as you can see, there are some important flags in there. So the first one I'm trying to set is the case sampling one. As you heard Ben talk about case sampling functionality of AutoML, this is how you use it. And then label column is obviously needed. And then I'm also turning on feature interaction flag, and I'm saying the mode I want to use is all. So you heard Ben talk about all, optimistic, and strict. In my case, it's all. The feature vector is going to be big, but it has been trained offline. So let's see what it looks like. Another configuration is I'm setting is scoring metric is F1. There are defaults for all of these configurations, and there are a bunch of configurations around AutoML that you can tap into. I recommend going to AutoML's public repo on the API docs. And if you have any questions on what each configuration is, you can go here and find it out and then tune it as much as you want. The next configuration is similar one, but instead of F1 scoring metric, I'm setting it to weighted recall. So I'm going to use this particularly for XGBoost. The next part is taking all of these 4 configuration maps and creating immutable Scala objects from them. So as you can see, that's what this cell does. And then I'm wrapping those configurations in an array, which are needed for family runner. The next step is I'm instantiating family runner. I'm passing in the training data set, and I'm also passing an array of configurations that we just saw. And then I'm just doing execute with pipeline API. It's that simple. Behind the scenes, it's gonna take all of the configurations, set up create Spark ML pipeline like semantics and concurrently run them on your cluster. So in this case, as you can see, it took a while to run. Normally, this is a part where I go and get myself a coffee. Depending on what your configuration is and what you're training, it can take a while. As we will shortly see, it's gonna it actually ran around 880 models for my 4 configurations that I'm posting. The next part is what we will do is we will look at some of the MLflow stuff that AutoML internally logs. So behind the scenes, AutoML logs every generation's parameters to MLflow, and then it also logs the best model that it finds in the end. So to that part, you will see that I have 2 experiments that have been created by AutoML. One is MLflow logs, and the other one is MLflow logs best. Let's take a look at what XGBoost generational runs look like. So as you can see here, it ran around 219 total runs. And as you can see here, we have around 12 generations that ran, and there's a clear generational increase in the metric success. So as you can see on the left, we have around 12 generations. On the right is an accuracy of around 98%. And similarly, we have it for XGBoost as well. So as you can see here, there's a clear trend of generational increase in the metric success here. So on the right, you can see it's around 97% for XGBoost. Okay, so now those were the runs for the generations. Now in the end, when everything's completed, AutoML also logs the best models for us. So we will see that if you click on this experiment, I'm looking at XGBoost. This is the best run for the XGBoost model. And as you can see, the pipeline API also logged some interesting parameters here. So it basically logs every stage because there are a lot of functionality around feature engineering that is part of AutoML. There are a lot of custom stages that we have that are not available in the standard Spark ML. So we have a lot of standard transformers that are part of the AutoML pipeline. And you can see that the best pipeline model that we are seeing here has some additional configurations that have been logged as well. So as you can see here, each stage has some interesting metadata around it. We can see what the input data set looked like. We can see what the count was. We can see what the schema was, what various transformations were. It comes in handy when you're troubleshooting and you are trying to figure out what each stage does. So all of that information can be found in your best run experiment for a particular run of that model. And as you can see here, there's plenty of stages that have been logged with all their parameters. And it also tells you how much each stage took. It tells you, sorry about that. So it tells you total stages executed are 25. It tells you what the execution stage is for each stage, for each of the pipeline stages. So there's a very handy instrumentation around pipelines that you can find here in case you're interested and you're troubleshooting something. Next thing is, I'm gonna show you, now let's look at what the return of the family runner looks like. So as you can see, this ran, it finished, and it returned back runner pipelines. So it looks like it returned back a map of string and pipeline model types. So it basically gives you a pipeline model, and it gives you, obviously it's the best pipeline model for each model type, and also the best MLflow run ID. So now you can use it to run some predictions. So in our case, the first recommended way is to do it by MLflow run ID. That way you're not messing with any of the paths, you're not manually loading any models. What this does is, as you can see here in cell number 24, I'm passing in the best MLflow run ID. and I'm giving some basic configurations that is needed to connect talk to the MLflow service. So it's gonna do a lookup on that best experiment name. It's gonna pass in the MLflow run ID. It's gonna read the MLflow tags on it, and it's behind the scenes. It's gonna find where the pipeline model has been written into. In our case, it's you can think of it. It's a basic. It does a basic lookup and loads that pipeline model for you. So that's all you need. In the next step, let's look at some of the stages of these pipeline models. So as you can see, a lot of AutoML specific custom transformers we have, um, and all of these are specifically written for AutoML, but they conform with the standard Spark ML pipelines implementations. So these are some of the custom stages for this particular configuration that we set. And then so all I'm doing here is, as you can see, by best pipeline model.transform, and I'm passing a data set to predict. And then it's just doing a display on it. As you can see here, we have a prediction column here. In our case, the prediction comes out to be a number, because that's what we provided in training. But if you actually had the actual label, the pipeline APIs will internally convert that into an index and then apply the indexer's index to string back so that the prediction is in the right label. The next part is running inference using the pipeline model directly. We don't recommend doing this, but for some reason, if you are not using MLflow, you can directly get access to the pipeline model that is returned by the family runner API. So as you can see here, I'm loading the logistic regression pipeline model and doing a transform on it. That's what this one does. And we can see here that we have the predict column. So those were, that's basically how you run inference, one of the two ways. Obviously, you want to use MLflow, but if not, you're open to using the pipeline model as well. Next thing is, I quickly want to talk about the feature engineering API. So if for some reason you're not looking to train and optimize with the AutoML's algorithm, you are free to use AutoML's advanced feature engineering pipeline. And that's what this allows you to do. So what I'm doing is I'm defining a basic configuration here that I need for my feature engineering. Again, you can go to the API docs on the open source AutoML repository, and you can find out what are the additional feature engineering steps you can use, like variance, covariance, cardinality. There's a bunch of stuff there that I would recommend take a look at before you start using it. So this is gonna do that for you. So you're passing in the configuration for running the feature engineering pipeline, and in the next cell 33, I am passing in that configuration, and I'm running generate feature engineering pipeline with the verbose option as true. So what this is going to do is, it's not going to train or run any genetic algorithm. It's just going to build your feature vector that you can then use offline to train a model with. The verbose flag is used for telling AutoML whether you want to see all the intermediate columns that were generated before the final feature vector was generated. So in this case, as you can see, the features vector is there, and you also have a bunch of additional columns. But if you don't want that, you can just turn it as false, and it won't do that for you. So it returns, again, the return of the feature engineering pipeline is also a standard Spark ML pipeline that you can use without needing anything else. With that, concludes this demo. I hope you enjoyed it.
And there you have it. That's AutoML at 50,000 feet. Yes, there's a lot more that we didn't cover. We have nowhere near enough time to cover any of these aspects or do any of it justice. But I encourage you to go out to Databricks Labs, check out the toolkit, download it on Maven. PyPy will be coming soon. Get involved. Help us fix all this stuff and implement it all. And look forward to seeing you online.